I think I'm recording. How do I know that I'm recording? There's no icon.
כן, כן, זה מקליט.
Okay, good. So the topic of the class today is radiation, electromagnetic radiation. It's, in my opinion, a beautiful chapter of physics in general, very important one also. So it's a bit unfortunate that you are all not with us today. I hope you had the energy to read the chapters of Griffiths and think about it, because it's really deep physics. So we all know that we can create electromagnetic waves that are symbolized schematically by this wave. We have this wavelength lambda, and we have, of course, the frequency of this wave, electromagnetic wave. And we know that for electromagnetic waves, these two quantities, one is the wavelength and one is the frequency, they are related. They are related by the speed of light, which is c. And all this comes from Maxwell's equation. It's one of the biggest victories of Maxwell's equations is that it can relate magnetism, electricity, and the speed of the light all together. They are all the same phenomena. We also know that these waves, these free waves, are transverse, and they are, I'm just reminding you now, there are three quantities, physical quantities, that are interesting for us. One of them is the electric field, E, which is now going to be time dependent. It's going to oscillate in time with this frequency omega. We have the magnetic field that in principle is also time dependent and spatially dependent. And we have the vector pointing S. So this is our vector pointing. It's going to be very important in this class today. Why is it important? Because what we're going to do today. Okay, so let me explain the general scheme of radiation. What is the general question? The question is, how do we create these waves? I mean, we saw that these are solutions, mathematical solutions of the Maxwell equation, but this doesn't say anything really on the creation of these waves. So this is done today. We will create these waves. So for example, we want to ask a question: how do we determine what is this frequency omega? The Maxwell equations, any free wave with frequency omega is a solution, but we want a particular wave length and particular frequency. So how do we get it? How do we produce it? This is a very basic question. The general question is also very important because, as you know, I'm transmitting now information from Bar Ilan to wherever you are, and I'm doing it exactly with what we are going to study today, with radiation. So radiation is not only some X-rays that you go to some medical device, which is of course radiation, but it is in a particular spectrum of the particular wavelength, that's X-rays. We have other phenomena that can be, for example, in the visible light. We'll talk about this later. That will depend on the frequency. And we can transmit different information with different frequency, microwave, etc., ultraviolet, whatever you want. So our course today is not very specific in what is the application. We are doing physics, and physics is much more general. But we have in the back of our minds that this is really important, transmitting of information through electromagnetic waves, whatever the frequency and with whatever the system. So this is obviously important for medicine, for communications, etc., for everything really in the modern life. So how is this created, at least in this lesson today? The idea is the following: we have some source. The source is something that is creating the radiation. And what is the source? The source is an antenna. The source is a ring. where you have some current. So let me plot it. So we have some antenna, which I will plot it like this. And exactly what I mean will become later when we go into the math. And this antenna carries a current. Let's say it's not charged. So there's no total charge on the system. It's a neutral system, but we do have charges. So we have some ions, which are in the background, let's say in a lattice. They are not moving, and the electrons are moving. Or we can have a different type of geometry, for example, a ring. But what I'm going to discuss is much more general than that. Actually, we will show towards the end of the class that any accelerating charge or system which has charges in it, whether it's neutral or not, will emit radiation. So what I'm going to talk about is super, super general. So this is what I have in mind, and this is what I call the source. And roughly speaking, far away from the system. So these systems have some length scale, which I'm going to call D. This length scale is the size of the emitter, the size of your system that produces the light. This is a new length scale for us. Well, not exactly new. We had, for example, the dipole. We had a length scale of the dipole D, and you will see soon that this, what we were studying on the dipole in the static limit, is also important here. And what is, so let us consider, for example, this ring. So we have here some current I of t. I is, as you remember, is a current in one dimension object. So in principle, we can have something more general like J of t inside the object. But the important thing is that the current is confined in space. It's in a small region in space. And what we are looking at, so here, let's say we are looking at the distance r. And our question is, what happens usually when r is much, much bigger than d? So why is this obvious? Again, this is obvious from our conversation right now. I'm sitting here in Bar Ilan. You are sitting, let's say, somewhere else in Israel, or maybe you are in some other place in the world, and I'm transmitting information, and my antenna, let's say, is small compared to the distance between me and you. So this approximation is very important. It's not only important in practical sense, it's also very good when we do calculations, because when this condition is met, it means that the geometry of whether you have a ring, or maybe you have something which is not exactly a ring that has some current inside here, these details will not be so important. It's again this coarse graining that we have. So we know that if we look, for example, on Earth, we look at the Earth from far away, it looks like a sphere. But of course, if we look at it from close vicinity of the Earth, we see mountains, valleys, etc. It's not exactly a sphere, but for a good approximation, when we are far from Earth, it's a sphere. And similarly here, only some generic feature of the system, which will be the dipole moment, which is time dependent. It's not the usual dipole moment that you are used to. So the general physical thing that will be responsible for the emission of this radiation is going to be the dipole moment of the system. But don't think about a fixed dipole now. We need to change our mindset and think about a dipole that is changing in time. Because if the dipole is not changing in time, the frequency of the oscillation of the dipole, then we have no frequency. So what is this frequency of the waves that are created? For example, in this context, let's assume this current is proportional to sine omega t. There is a prefactor there. What is this? This omega will turn out, this is what we are going to show, this frequency of the motion of the electrons in this small ring, or the motion here up and down this small antenna, with the frequency omega, this frequency here will determine this frequency. So if you have some way. For example, applying a voltage on this system. And this voltage now is time dependent and it's oscillating with some frequencies. So you can create a current. This is easy for you to understand. You can create a current in a system which has frequency omega. Well, this frequency omega will generate the radiation at the same frequency. So this is how we choose the frequency. We have some currents, they have a frequency, and this can generate this frequency. Now, of course, as a theoretician in this class, it's very easy to say, let's generate in a ring some current with some frequency omega. Of course, this will depend, can you really do this? That will depend what frequencies you are. For some frequencies, it's rather easy, but for other frequencies, it can be very difficult. And this is related to the fact that the spectrum that we can generate is limited in some sense. We cannot go to extremely high frequencies, but still there's a huge range of frequencies where this can be done. And this control of the physical system, this frequency of this oscillation of the current gives you the eventual frequency. But radiation is, again, much more general. You don't need necessarily a sine or something oscillating in time. This will be the first part of the lesson, something periodic that generates a free wave very far away and also long after we turned on the system. So you come to the system at time t equals 0, then you switch it on. At the beginning, there is a wave propagating, of course, far distance. You do not see the turning on of the system because things propagates at the speed of light. But after some time, you continue with these oscillations. You generate this wave that in principle will stay there forever if the frequency of this physical system, is remaining. Okay, so this is the general framework. This is the physical question. What is going on in these type of systems and what is the meaning of this radiation? If you have questions, please ask. So we will use this approximation. I will call it later maybe dipole approximation. You'll see the reason why. So now let us be a little bit more specific. Let us think about it. We have here our source. Source. We said its size is roughly d. We also said we are interested in some long distance. So let's say the origin is somewhere here in the middle, and we have the distance r. At distance r, we have the observer. So if I am the source, you are the observer. That's the distance. Let's say you live in Petah Tikva, 10 kilometers from here. Much, much bigger than the size of my source, okay? The question is, what is the radiation going? So what is radiation at all? So first of all, before treating the systems, we have in the system some ER and T and BR and T. Why do we have this? This is obvious because in here, in general, we have some current J. Maybe we also have some charges that are moving here. Maybe it's charged, not charged. This is not so important right now. And these create electromagnetic fields. This is obvious. This is trivial. These are E and B. Then the question is, what is the flux of energy? So what we care about is the flux of energy. A flux of energy, if I throw on you spheres, some small balls, I transmit kinetic energy to you guys, and then possibly if it's just transformed into heat, you will get heated, so to say. Here we are sending electromagnetic fields, but we know already from previous classes that these fields, especially if I take E squared and if I take B squared, this gives you the density of energy in space. So in some point here, there is some electromagnetic field, E, and some magnetic and some electric field, and these give you density of energy. And these are changing in time and space. It's very complicated depending what are these fields here. We also know that by integrating overall, let's say all this sphere here, because these fields have an energy density, we know that the whole system at some given time t has some energy, right? We studied about it. You just need to integrate the energy density, E squared plus B squared with the E0 and mu zero. You do this integration. So here inside there is energy. Now this is a huge, huge opportunity for anyone who is, let's say, at the beginning of the 20th century or end of 19th century. Wow, there is energy. Let's do something with this energy. This is what Edison did. He made light, right? He's producing light. Okay, so the idea is that energy is conserved, of course. But we know that we have here a source that is pumping energy into the system. I'll come back to this. So the energy, you are giving energy to the system somehow with this I, which depends on time t. So what is happening to the energy? It's flowing outside. The energy is flowing outside. And then this is good, because if you are here at the observer, well, you'll receive this energy. How will you transfer this energy into something useful? Well, what is this energy really? It is related to some electromagnetic field. So I have an antenna that is emitting. You have some antenna that is receiving. And then we can communicate from far distance. Modern world is arising. That is the modern world, not quantum mechanics. It's also the modern world, but this is the real modern world. We can do that. I think you can start understanding this, and you can see that this is really beautiful and important. Okay, so now we have this emission, but what is the physical quantity that will quantify this? That is what I said just now is nearly obvious for anyone who is holding a cell phone. What is the important physical quantity that will quantify the flux of energy? We also studied this already, and that is S, the Poynting vector. So we studied already that, we know already that the change on the total energy in a region, in this region R, there's flux of energy going outside, and this flux of energy is given by the vector pointing S. Again, we had it. What is S? S is E cross B divided by mu zero. I'll write it down soon. So if I know the E electric field, I know the B, I know the S, I know the flux of energy coming out of the system. What is the flux of energy now? The flux of energy at this point can be different than on this point. I'm talking about the flux of energy at radius R. So at this point, let's say where the observer is, I will have a small patch. The size of the patch is going to be dA. This is a unit surface. So what you need to think about is a sphere. The sphere, on the sphere, I have a small dA. Of course, this dA was in this course. You all know how to relate it to, let's say, spherical coordinates. This is very standard for us by now. Now, through this A, there is a flux of energy. And again, at this point, at this point, the flux of energy might be different than in other points. So another question is, if we have here this antenna, is it emitting in this direction, or is it emitting in this direction in the same way? That is one of the questions we want to know, because if we have some small dipole that is emitting, we want to know how to put it in line with the receiver. I mean, if we put it in the wrong way, the receiver will not get any information. That's bad for us, right? What is the maximum way? Should I put oscillate like this or in some other direction? That is a question that we are going to answer. But anyway, the light, the energy, the radiation energy that is spread out here is not uniform on this sphere. So what is it? This energy, I claim, is S. It will be actually an average S, dA. S again is, sorry, dA. What is S? S again is the Pointing vector. Average S is because this we'll see later. This S is actually oscillating over time very quickly with a frequency omega. We're going to average this. So this average will come later. It's a bit important, but it's not the essential thing. In principle, the radiation itself, the flux of energy itself is fluctuating in time. But this, if you coarse grain, the person who's receiving the information is averaging by the method that he's receiving the information over time. It's not so important that we will get this average S is going to be some constant independent of time. Again, this is a fine detail. So we need to get this vector pointing, and we need to calculate SDA at a given point. So this S will depend on where you are on the surface. There is another power, in Hebrew, hespek. Sorry. What is the power? The power is the energy per unit time. So P, not to be confused later with dipole moments that are also P. This is a scalar. It depends on R, and this is the power P is the energy per unit time. What energy per unit time? That is emitted all over the sphere. Now I'm averaging over all the sphere. So SdA integration over the surface, for example, of our sphere. What is this equal? This is, of course, vectors. By definition, this is the vector pointing. This is the surface of the sphere. E cross B, that's the vector pointing. This is the object that we proved previously that gives you the flux of energy coming out. I hope all of you remember we started with conservation of energy. In this discussion, we proved this. So this is the vector pointing. This is my S. So the point here is that there are two observables that we want to calculate. One of them is the local S on the sphere that changes from point to point. So this will depend where you are on the sphere. As I said before, here and there, the answer is not the same. But I can also calculate the total energy per time emitted all together. When will one observable will be imported? When will another observable will be imported? Of course, if you are sitting here and you want to know what is your flux at this particular point here, you want the local S, the S that is related to that particular point. Then if you move somewhere else on the sphere, you want another S, let's say down there. On the other hand, you also want to know the total energy emitted per unit time. Why do you want to know it? I think it's obvious, but if you know the total energy that is going out of the system per unit time, you also know how much energy you need to put in the system in order for it to go out, right? So if you just want to know, how much energy I need in order to generate this beautiful physics, I need to know the total energy that is emitted. Now, where does the energy come from? Of course, the energy is conserved. It comes from the fact that here I have these currents. The system, of course, has some resistance, and to maintain the frequency of oscillation, this omega that I had before in these oscillating currents, I need to put in energy. And some of this energy goes to heat, and some of it goes to radiation. What we like about radiation is that it can go far away. On the other hand, the heat that is also generated, unfortunately or not, is staying in usual circumstances inside the system, and it's just heat. It's not useful for us. What I'm trying to say also is here I have a vacuum, of course. I'm not going to discuss the case where there is some material in between. That usually will disturb us. You will have some scattering and the transmission will not be as good. But we know that air is, at least at distances that we are discussing, like 10 kilometers, 20 kilometers in usual radiation schemes, is good enough, but not always. Sometimes scattering is very important. And then these rules are not good enough that we are going to discuss. So there is no scattering, no absorption in our discussion right now. So now we know what we need to do. We need to calculate S. Questions? Now let us see some magic. And let us think about this. What do we want in order for transmission of information through radiation? What do we need? Let us think about it a bit. What is dA? dA already in this course is something very standard. It's R, and the important and maybe only important thing, squared here. Of course, we saw squared many times in this course. This is well understood. But this is the element of this dA, this small patch that where I'm looking at the local S. We have d cosinus theta, which is not so important for my discussion now, d phi r hat. So you know that the direction of dA is perpendicular to the sphere on which I put my observer. That's the directionality of r. Okay. But now I want this PR. It's not that I want. This is the magic that is going to come out. This is the magic that you can use your cell phones, etc. What is my demand now of S? Now in absolute value, I'm not looking in directionalities, no mathematics now. What should be S in order for the power, P, to remain finite? What do I mean finite? Finite at large distances. Remember, the integration here is over the sphere. R is fixed in this integration. So what do I need from S to get something really beautiful? Can anyone answer?
1 over r squared.
Good. We need, let's put a question mark at this stage, 1 over r squared. If I get 1 over r squared, welcome modern world. If this is not true, we cannot communicate. We cannot have x-rays, all the beautiful things that you take for granted, but it's not so obvious. So we need this.
Can I ask a question?
1 second. We need this, and we will prove it. But first I want to say how unusual it is. What do we expect? Let us assume that we get this 1 over r squared. Later we will going to prove it. What does it mean on E? Again, absolute value. What is E? How does E behave? Let's assume there is some symmetry, and also B will behave like that. Let's assume it goes like 1 over r, and this guy also goes like 1 over r. If this is correct, then we have our cell phones, right? And then again, I'm going to prove it. But why should E fall like 1 over r? It's very strange from static point of view, right? Why? Because let's assume that the density is 0. There are no charges, no net charges on our system. So this is the source, and it's totally neutral. There is some current, J, but it's neutral. In electrostatics, what is going to, okay, let's say it's even charged. what will be the E if it's charged? What does Coulomb law say?
1 over r squared.
1 over r squared. So we want something that goes like 1 over r, or more correctly, we get something that will go like 1 over r, even if the system is not charged. This is a very slow decay. Very slow decay compared to Coulomb law that is 1 over r squared, or compared to an exponential decay or whatever decay. This is so magical that you can get excited about this. And this is what is going to happen. And of course, all this is related to, first of all, Maxwell equations, but also obviously related to relativity, to the fact that the velocity of the speed of light, c, is finite. So this is the magic. And this is what we are going to look for when we do the math. In this case, the P radiation limit when r going to infinity. Of course, this is valid only because I assume a vacuum around the source. There's no absorptions, etc. P of r is finite. Long distance radiation. Of course, there is also an obvious condition. It's not that I can transmit light faster. So there is a time t, let's define it now as, it's not the general time, but some time t divided by r over c when we turned on. So this is the time after turning on the system, turn on at 0. After this time, the radiation will reach, but we are talking about times longer than that, much longer than that. So the radiation already reached, it's not 0. The turning on is not important, as I said before. That was in previous class and also in exercise home. So this is the general scheme that we are interested in. If there are questions, let us, because now we are going to solve this problem in 2 ways. One with a pedagogical example and then with a general method.
Yes, I wanted to ask why it should be specifically 1 over r squared and not, for example, 1 over r in the power of 3. It's still be finite in this case for big r's.
No, because because this is what I tried to say, but I'll repeat. The integration here is over the surface. It's not over the volume. Why am I integrating over the surface, over the sphere itself with r fixed? Because I'm interested at each point, delta A here, delta A here, delta A here. What is the flux at these points? R is fixed. And then I'm summing them all over. Okay?
But if the pointing vector will be 1 over r in the power of 3, and you will put the big R, it will still be finite. It will be 0, but it will be finite.
No, because of this r squared. So r squared divided by 1 over r cubed is 1 over r. 1 over r is not good.
Why not? That is my question.
Because imagine that I communicate with you and you are very far away and 1 over r, so you agree that 1 over r is much, much less than a constant.
Yeah, sure.
When r going to infinity at a very large distance, 1 over r is 0. That's all. 1 over r is 0. So you are right. Maybe I understand where your maybe confusion comes from. And that is, we said that 1 over r is a very slow decay. It is true. But we are talking about the 1 over r of the vector pointing now, and 1 over r, 1 over r cubed is a slow decay possibly compared to exponential decay, but still, it will not be good enough. You can say, okay, I don't care, 1 over r to the power, let's say 3, I can come very close. And then I will we will be able to talk to each other. But no, I don't want that. I want to really, independent of R, no matter how far you are, I can in principle communicate with you. That is a big wow. Okay, any more questions? Okay, so now we want to start dealing with this, and because this is a complicated issue, which has several steps inside, we are going to start with a pedagogical example following Griffiths. So the pedagogical example is, we first define the z direction. I'm now defining the source. In some sense, I'm defining the current, which was I of t before. And the current here is actually a bit strange, but it's very useful from pedagogical point of view. We have 2 points, minus q and plus q. This is up, this is down. And these q's, they are changing in time. So the q of t, this is a charge, the unit is coulomb, is q0, some charge, multiplied by cosine omega t. Again, omega, as I said before, is a frequency that the experimentalist is putting in by hand in the source. And this frequency eventually will be the frequency of the waves that we are creating, okay? So we know what is Q0, or we can control them. We know what is omega, in principle at least. So what we are thinking here is that we have here a very, very thin wire connecting between the two. And this wire is kind of sending the charge from the bottom to the top. Because we have here a minus, and in the top we have a plus, then we know that the total charge here, total charge is 0 at every given time. There is no charges, and hence what I said before, that eventually the fields are going to decay very like 1 over r, E and B, is very surprising. I mean, it's slower than, it's going to be slower than Coulomb. Now, in this system, as I mentioned before, we also have D. I'm going to define the origin of the system exactly in the middle. So this distance is obviously d over 2, and the same, the other distance, minus d over 2. This is the positions along the z direction. The z is going up together with this dipole. So I think everyone sees that we have a dipole that is changing in time, and we can define the dipole P of t as Q0 times d cosine omega t. And again, this P, not to be confused with the power. This is a vector P. This is a dipole. And it is pointing in the z direction. So by doing so, we broke the symmetry of the system. There is a preferred direction. This is our current. And then when we look here, there is a z direction. And then eventually current here or here, sorry, radiation here or here will be different. There is another definition, which I'm going to use P0, and that is Q0 times D. That's the maximum value of the dipole. This is going to be a useful quantity. And if you want to think about it more mathematically, maybe the way to look at this is Q0 goes to infinity, D goes to 0, but Q0D is a constant. I say this because at this pedagogical example, I'm not treating the current inside this wire. They are so close there is some charge on top, on bottom, and they are very close, but eventually this is going to be finite. This is P0. But this is just if you are inclined to some rigorous mathematics and precise definitions of what we are doing here. The generality will come later where I use some general J. So obviously here we are dealing with a very specific example, but still it's a very instructive example. Now we need to define some distances. So we have these, this is the origin, and we define R. This is the position of our observer, which before it was on the sphere. This is the vector R. And then there are two distances, R plus and R minus up here. Now, this figure is not to be taken in reality. I said already that D is much, much smaller than R. R is very big compared to D. D is this distance. So we immediately know what is R plus and R minus to zeroth order approximation. It's simply R because R is very big. I hope you all see it. So R plus and R minus have, to the first approximation, they are simply the distance from the origin to the observer. And we will need to calculate some corrections for that, which I hope remind you of something. And this, what does it remind you of? Something that we studied. And in addition, I'm going to define this angle theta. So this angle theta is the usual angle in the spherical coordinates, r, theta, and phi. So I'm using spherical coordinates. And of course, going up, that's the z direction. So theta gives you the projection on the z direction as usual. So now we need the retarded potential. The retarded potential and its potentials, because we have two potentials. One of them is the scalar potential, V, and the other one is the vector potential, A. We need both of them. Again, I remind you, this was in previous class. In previous class, we showed you, in principle, how to solve Maxwell equation in full generality. We got these linear, the potentials. Maybe I didn't use this word and this confused you, but that was previous chapter, V, R, and T. I'm going to write it down soon. If I know these potentials, as usual, I know the fields E and B. And if I know E and B, I know S. And if I know S, I know the power. That's how it goes. V, A, E, B, S, P. All these 4 steps need to be done in order to calculate the total power. So what we are going to do is the following. We're going to write down this system. So what we have here is R plus. We have here, in this example, R minus. And we have this theta. And we have this distance D. And let us write VR and T. This I'm just taking from previous chapter that we studied last week. 4 pi epsilon 0 rho R prime T retarded R prime minus R absolute value d tau, integration now of the volume, not of the surface now. We are integrating over the charge density inside the system. We are soon going to say, what is the charge density in our system? What is it? What is rho?
0 should be.
No, it's the total charge is 0. But the charge is not 0 because I have 2 charges here and here, which are Q and T. So the charge, this rho, it's a charge density, is composed of what? Of 2
Deltas.
two delta function on these two positions. We'll soon write it down. But the important thing to remember, which is still, maybe you are still thinking about this deep physics, is this R. R is for retarded, right? TR, the retarded time. So this equation is the same equation that you have in statics, but instead of using the local time, the time where you are measuring, time t, you are using the time tr, which is the time where some charge emitted light and the light arrived at the detector at point R exactly at the right timing, giving you the effect. So this tr is depending on, first of all, on where you are in space, on this point, how far you are, and also in general on R prime, where in the system you are integrating. So here I wrote it in general. So imagine some system with some J, then I need to have the charge density here inside, or the J, and you need to do this integral. So what is this rho R? I'm not specifying yet what is the retarded time, but I'll soon give it to you. So what is this PR prime that I need to integrate here? As we said before, it's a sum of two delta functions, cosine omega, the retarded time. This is just, I'm taking here the definition that I need to look at it at the retarded time. Delta R prime minus D over 2 Z minus Q0, blah, blah, blah. This is charge on minus D over 2. So the minus here, this minus, is because the position now is plus D over 2. And you'll have a similar expression, but now with a plus for the other charge. Again, this is the charge here and the charge here that depend on time. I think this is obvious. When you insert it and take into the fact that we have delta functions, these delta functions, by the way, help you tremendously. It's not by chance that we are using this pedagogical example right now, because integration over delta functions, here, this integration over the whole volume, this is the whole volume for whole space, is very simple. Even I can do integrations over delta functions. And I'll just give you the answer after integrating the delta functions, and then we will discuss this solution. The potential that depends on where you are in space and depends on time is 1 over 4 pi epsilon 0. It's going to be a long expression, but not too long. It's Q0 cosine omega t minus R plus over C divided by R plus minus Q0 cosine omega t minus R minus C divided by R minus. So what do we have here? This after integration is a kind of retarded time. It's not in the integration, it's after the integration. So this is what is R plus over C. It's pretty obvious. We have here, this is the plus, the upper charge, this is the minus. We have this distance R plus, and our observable, this is where we put our observation point. So R plus over C, what is it? It's the time plus. Time plus is time to transmit information from plus to the observer. So what do we have here? We have here the charge, not at time t when you are looking at the system. Time t is the clock that the observer is using. We have the time at the previous time, at the retarded time, t minus r plus over c, because this is what we care about, simply because the light has a finite propagation. And similarly with r minus, this one is with r minus, this is with r minus, this one is so this is the retarded time. It's not exactly like tr because I did already the integration. And of course, there are some differences between r plus and r minus. They are nearly the same, but not exactly the same. And these distances are what we are going to analyze now. Any questions? This is an important formula in our course, in our lesson today. Now, what we need to do is analyze this equation. And we do it with the cosine theorem that you all saw millions of times. So for example, I have here, this is the origin, this is d over 2, this is r plus, and this is r, and this is theta. So I want to know r plus. I know theta because theta is defined by where I put my observer, right? If I put the observer somewhere else, I'll have a different theta, a different r, but theta and r are controlled. These are the good variables, r plus. I'm going to express now in terms of r and theta, and of course d over 2. And this is very easy because r plus and minus by the cosine rule is r squared minus plus or minus, because I have both r plus and r minus. I think you remember this. 2r d over 2. Of course, the 2 will cancel. I just write it in the suggestive form, cosine theta plus d over 2 squared. So this is the cosine theorem. And we have now the distance expressed in terms of r plus and d and theta. Now, we are interested in this limit where r is much bigger than 1. So this is our approximation number 1. If we have this approximation that we are looking far away, we don't care about the small scale distances, then we see immediately we have here, of course, the leading term is going to be this one. So this is like the 3 golden locks, you know, the papa bear, the mama bear, and the little bear. So this guy is the small. This guy is big. This guy in the middle is intermediate, not big and not small, he's just right. This is the important term that we will be looking at, while we will throw away this guy completely, again, because the r is very big compared to d. So we can easily Taylor expand, and you know how to Taylor expand. So I take this r squared outside of the square root, and then I will just write it like 1 minus d over r cosine theta. And then there is another term that is just going to be smaller. And this guy is more or less equal r, which is the leading term. So again, r plus minus to leading order is simply r, which you can immediately see. And this is, here I have minus plus half d over r cosine theta. Where did the half come from? It came from the square root when I did the Taylor expansion. What does cosine theta remind you? Well, we'll soon think about it. What is 1 over r plus and minus? I just have to take this and do another expansion, a Taylor expansion. So it will be 1 over r. This is from here. And then I have 1 over this square root. Then I need to expand it again. And then I have 1 minus plus minus. So before it was plus minus minus plus. Now it's plus minus plus minus. Why? Because I need to have 1 over the square root, and then I expand it, and then I get the switch of the signs, and then I get another half d over r cosine theta plus other terms. Okay, so where did we expand 1 over r plus and 1 over r minus in our course? And what does this remind you? In statics. What is cosine theta? What does it?
YLM.
Yeah. So no, the Legendre polynomials. So
Yes.
we did a similar expansion when we did the dipole approximation in the static case. And what I'm doing here is the same. I'm doing an expansion which is called a dipole approximation. So all the theory, we can call it as a dipole type of an approximation, but it's very different than what we had before, because now we have the time, we have the velocity of light, c. So it's a very different type of approximation, but in spirit, some part of it is similar. So this cosine theta is going to be important later. Let's call this Aleph. Okay, so now what do I really need to do? I go back here and I have this cosine in the retarded time. Let us look at this cosine in the retarded time, for example, for the r plus. So we need this cosine omega t minus r plus over c. And we need to approximate it based on the assumption that we had before. So what is this? Let us write it first down explicitly with r plus, with this correction. You see here I have a minus, and then I have another minus. Then I have this. This is going to be cosine omega t minus r over c. This is very obvious what I'm saying here. I'm just saying here the leading order inside this cosine is simply r plus is r. Again, because we are far away, r plus is r. But then there is a correction, and the correction is omega d over 2c cosine theta. All this inside. This is coming from this. You see the r here and the 1 over r here, they cancel each other. So this expression does not depend on r. It depends on w over c. What is w over c?
A?
No, it's not a. What do you mean w over c?
K.
K. Yes. I didn't hear so well. Yeah, so this is related to the wavelength of the system, to k. At this stage, it's not the wavelength, not exactly the wavelength of the radiation. It's just in these equations, but you see it popping up. And indeed, at the end of the day, this will be the wavelength, as I'm going to show. But this gives you already here a new length scale. So how many length scales do we have? We have d, we have r, and now we have 1 over k, which is lambda. So we have 3 length scales, r, d, and lambda. This makes the problem complicated. We can choose the length scales to be bigger one compared to the other. And we are interested in only one choice of the relations between them. We already said r is much bigger than d. So all we are left with is what happens with lambda compared to these two length scales. It's a very important physical point here. That is actually determined usual circumstances, but not all circumstances. It's determined, let's say I have frequencies and immediately the velocity of light is given. So let's say the frequency is 10 to the 15 hertz. So I know exactly what is the lambda eventually. So I have limitations. If I have frequency, I have immediately this lambda. And then if I know the distance, at least to the observer, I can immediately say, is lambda much smaller than r or not? Of course, r is going to be much bigger than lambda. That's large distances. So r is bigger than lambda, is much bigger than d. The question is, what is the relation between lambda and d? That we will soon state. But okay, let us state it now. We're going to assume that D is much, much smaller than lambda. So again, omega over C, we define it as K. We define it as 2 pi over lambda. That's the usual definitions. And this is approximation number 2 that we are going to use. And this is going to be important later. So let us look at the plus term in V. So again, I go back here. What I mean by plus term, this is the plus term with the plus. The other term here, this is with the minus. I'm looking at one of them. We can call it V plus. Of course, how will the other one behave? It's very simple. It will behave exactly the same, but every D you need to replace with, if one charge was on plus D, the other charge was on minus D. So all you need to do for the second term will be to replace D with minus D. That is very easy. I will not go into all the details. So what is this V plus is 1 over 4 pi epsilon 0 Q0 cosine omega t minus the retarded time omega times the retarded time. The retarded time is everything, t minus the delay time, r plus. Yeah, this is exactly what we had before up here. And what did we gain up till now? We have 1 over r plus. We know what it is. We have r plus. It comes in here. This r plus is given by this cosine, complicated cosine, a cosine of a cosine. It's pretty ugly, I agree. So let us still do this and find out what we get. So what is V plus? Okay, 1 over 4 pi epsilon 0. And now I need to expand 1 over r plus. So what is it? Let me write it down. It's 1 over r 1 plus d cosine theta over 2r. More terms. So all this is 1 over r plus. Okay? I expanded this. Now I need to have the equation that we had before. It's too long. This equation for the cosine. I need to copy it, unfortunately. Let us first simplify. Okay, so let us write this like this. And first, we'll come back. So leave some empty space. Let us look at this expression. So we have this cosine. I'm writing down already after again, this is the leading term. This is simply r plus is equal to r, and then I add d over 2c cosine theta. All this inside the cosine. Now, let us remember maybe you remember it, but I like to do it like this. What is the real part of exponential of alpha plus I alpha plus beta? You know what this is. This is cosine, because I have here cosine. This is cosine alpha plus beta, right? And this is also equal. It's, I think, easy to say, sine alpha sine beta plus cosine alpha cosine beta. This is, of course, a very famous equation, but if you don't remember it, you can use this. So if I define this as, let's call it cos, then this is equal to the following lovely thing. It's equal to cosine omega t minus rc. That's my alpha, so to say. This is this alpha here, multiplied by cosine omega d over 2c cosine theta This is my beta here. Then I need to subtract. This is this minus here that I have here. Sine omega t minus RC multiplied by, this is multiplication, oh, I'm so sorry, sine omega d cosine theta divided by 2c. You love physics, don't you? Okay, so what is the leading term? You see immediately, this is the leading term. We are going to assume, as I said already, that d is much, much smaller than lambda. But this is exactly here, d over lambda. So this guy inside is small. What is this guy? This guy is also small. What is the cosine of a small number?
1 minus half x squared.
Yeah, but let's be lazy. So the leading order of this cosine is 1. And then this is equal to cosine omega t minus r over c. And again, this is actually trivial. I'm emphasizing this. This is just replace r plus with r. This is the zeroth order approximation. This is what we say. This is something which is the leading order correction. And then we have this first correction, sine omega t minus rc. This comes from here. And then what is small sine of a small thing? I can expand it. So I expand this sine omega d cosine theta divided by 2c. This is what this cosine enters eventually. You see it enters up here. Now, what did I do? It was mentioned before. So what I'm doing here is some cosine, let's call it x, is 1 minus, as the person said here before, x is much, much smaller than 1. What is sine x? Is x. I'm neglecting these terms. This is why I did not expand it to higher order here. But I'm not neglecting the linear in x terms, which come here. Okay, so this correction is the leading. So this is the leading, which is a trivial term. And then we have the next correction. Why do I have to calculate the correction? It's trivial. Eventually, let's say d is equal 0. The two charges are one on top of the other. Plus qt and minus qt together, they are not oscillating. What is the radiation? 0, of course. So what I need, and what is important, that this term depends on d, while the first leading term does not depend on d, and hence actually the important term is the correction term, when we will add the other contribution that comes from this v minus. Remember, this is only for v minus. So summarizing all this together, let's write down what is, we go backwards. So now I go backwards, sorry for this. So here I have to see this. So here is just the declaration of the result. I multiply it by cosine omega t minus r over c minus sine omega t r over c omega d cosine theta over 2c. Okay? So this is the v plus, and we have a similar for v minus, similar for v minus. Just take d to minus d, which means this minus sign will be changed, and then you can do the math easily. Again, this is small. This is because, again, the wavelength is much bigger than D. Actually, this is usually related to, let's say, a molecule that is the dipole. So maybe not a big antenna. Maybe what I said at the beginning of the class is a bit misleading. The molecules, small molecules, are going to be the antennas. Later, there is a different approximation where it's the opposite, but I'm not teaching it, unfortunately. That will be a little bit different physics. Okay, so now we have everything, and then we can summarize the total potential, V. It's the electric potential, is P0. Again, P0 is Q0 times D. It simply comes from, it comes from the charge inside, in front. We have the charge in front. Oh, vey, oh, vey, oh, vey. Here I have Q0. So P0 is Q0 times D. This is what I called before the amplitude of the dipole moment. D is the distance between these two charges. Q is the charge. So this is obviously a dipole moment multiplied by cosine theta 1 over R. I think you see where the cosine, or remember, you see this cosine theta appears everywhere in the expansion. Okay, 4 pi epsilon 0, 1 over R. And here I have minus omega over C. I'm switching the order, actually, what we had before. Omega T minus RC. Again, you see here the retarded time. It's not the local time, it's the time where we use the approximation that R plus is R to leading order, plus, this is all in the parentheses, 1 over R cosine omega T R over C. And the important thing to understand now is actually I'm switching the first approximation. This guy was the leading order, but now this is going to be small. In what sense small? You see here, what is W over C again? This is 1 over lambda. And I'm assuming the following, that D is much, much smaller than lambda, is much, much smaller than R. So from here, it's obvious that R is the big parameter. You are very far away from this emitting object. And then this is 1 over lambda here. And then what eventually turns out to be is 1 over lambda. And already here you see some beautiful magic. Why? Because you see this term is 1 over R. This term, okay, let's put it more correctly. The second term, this term, is 1 over R and 1 over R. The first term, this one, is just 1 over R term. Maybe it doesn't give you, so it's very important because the potential is decaying slower in this term compared to the second term. And this very slow 1 over R is going to save us, and then you can have cell phones and you don't need to come to the university and see me. What a tragedy. Okay, so this is, already here you see some magic. You also see the magic in this C here. If C would be infinity, then this term that is independent of R, this one, again, there is an R dependence outside, but compared to the other one, this C would be infinity, no effect. So the fact that the speed of light is finite is, of course, super, super important for us. If it would be infinity, then we would be in a bad shape. And then we can continue. So what does this condition that I'm using all the time? We have this lambda. And this is, of course, this lambda, as usual, the usual definition. So what I mean is, of course, that R is much, much bigger than C over omega. Now, if that is small, then VR theta and T, this is just a way of writing. The potential does not depend on phi, because around this antenna, this dipole, there is a symmetry in phi. So you have a dependence on theta, and you have a dependence on R, and you have dependence on time, but not on phi. This is equal, which I can call a dipole oscillating, if you want, minus P0, that's the dipole, omega over C, 4 pi epsilon 0, cosine theta over R sine omega T minus R over C. And this is this approximation for this thing. One comment. So simply what I did here is I forgot about this term, this small term. I threw it to the trash can. And later on, if you are, let's say, physicists in the beginning of the 20th century, or you are engineers, and you want to find corrections, I'm not saying they are not important, but they're not important right now in this class. I also want to emphasize one point. What happens if frequency is equal to 0? If the frequency equals 0, what do we have? We have a static dipole. And then you see that the leading, what I eventually took as the leading term will totally vanish. This term will vanish. And the cosine here, which depends on time, what will happen to it? It will be just 1, because cosine of 0 is 1. And then you are left with V equal P0 cosine theta 4 pi epsilon 0 R squared, and that is the static dipole. Of course, in our problem, we don't want frequency equals 0. That is going back to the beginning of our lessons, where I took the time and liberty to teach you this dipole approximation. So hopefully now maybe you understand why I taught you. This is very important to memorize, and I think by now you know that this is the dipole. Again, this is the polynomial Legendre cosine theta in the dipole approximation, and then we have this R to the power 2. R to the power 2 means that the electric field decay like 1 over R to the power 3, while the leading term here will give you something better. Now, there is another subtle remark. What we actually want to calculate is E. And so this is subtle, a little subtle, not really very subtle. I'm not going to calculate E right now. I'm going to do it later. This is equal d over dr, 1 over r, d over d theta, theta. I'm using here the divergence in spherical coordinates. Okay, there are phi derivatives, but we don't care about them because the expression is for the potential is independent of phi. So we don't need to consider them. Now maybe it's a bit stretched, maybe you need to do it by yourself, but let us look at this term. Is it a good term for our purposes? Of course, all terms are good. I'm not going to insult any term, but is this a good term for our purposes? You see that this derivative with respect to r, there's this prefactor 1 over r, and that will make the field coming from this term even smaller. So we have d over the theta. The only theta is on the cosine theta that is here. That will give you a sine theta, which will also appear later, but this will give you 1 over r. It's going to be a small term. What about this term? What does it give you if you just look at this like this? This term gives you, what is the direction? Obviously, it's R. Is R direction a good direction? Good, not, I'm not judging it. Good for our purpose. Is R the good direction? What is in our direction, our hat? We know the physics, at least. I think I told you previous classes. What is in our direction? Remember the sphere at the beginning.
It's the direction of the area.
It's the direction of the area and the direction of the vector pointing, the physics. The vector pointing is going in that direction. So the E and the B are perpendicular. Sorry. So this is S. This is what we expect, or maybe I saw this too many times. So I'm expecting EBS. So this direction that you get a component of the field in the direction of S. And you know, because I taught you, that for a free wave at least, E is perpendicular to B as it perpendicular to S. Correct? I taught you this, guys. You remember this? So what do we get here? We get here a term that is small because of this 1 over R, and a term that is going in the wrong direction. Now, if you read, as I asked you to, Griffiths, maybe you know the answer. So what is missing here? Why this is not, it's a small cloud and nothing more.
Maybe the vector potential.
Exactly. So in this argument that I just hinted, I didn't do the calculation because we don't have time, but we also have A. And previous class, I told you what gives, for example, the electric field, both A and V. A, you take the time derivative. V, you take the divergence as usual. So what we will get eventually is some cancellations of all kinds of terms. For example, the term in the R. And actually the main contribution will come from the A. So it's a bit subtle, but this is bookkeeping, algebra. Again, if you want to go through the details, it's not complicated, but I'm just pointing out that many subtle points here along the way that we cannot go through all of them, but you should by reading Mr. Griffiths. So, okay, so now I remember I need to calculate A. This is going to be a general equation. I'm actually not sure I gave it in the previous class, but this is a super important general equation that I will explain now. TR R over R prime. It's not specific for our problem, d tau. Oops. Sorry. What is this equation? It gives you the vector potential in terms of the current density J. This equation is very familiar for you. Now you thank Griffiths, and maybe you even thank me that I taught you this equation in the static case. Because in the static case, it's exactly the same. Just you have to replace this TR by some static current, which means that it doesn't depend on time. So this is the usual thing. You can say legitimately, this is the Biot-Savart law that you studied in high school. The only difference is that now we have this retarded time. Well, it's not a small difference, it's a big difference. But the formula is exactly the same, exactly like the formula for the potential V is exactly the same as before, that you need the charge density rho, the equation that we started at the beginning of the class. So let us just remind ourselves what it means. It means the following. Again, this is my physical volume in which I have some charge some current. The current is changing in time and in space. So J is a function of R and in principle time t, local time t, but eventually you need to put the retarded time t. And then I am looking as usual at some person that is far away, and I'm asking what is the potential, the vector potential A, and this is given by this equation. How do we get this? We get it from the Maxwell equation. So this is the solution of the Maxwell, the formal solution of the Maxwell equation. More specifically, if you remember the last lesson, we get it from the D'Alembertian, another French guy, which had this strange operator that we had last lesson, and we use the gauge of Lorentz with a Z, no T. This poor Danish guy who's a great physicist, but he was overshadowed by the famous Lorentz, who's a Norwegian one. So yeah, if you have a name and it's like a famous one, maybe you should change it. Otherwise, no one will remember you. Okay, don't worry. Also, no one will remember me soon. Anyways, so this is this equation. And as usual, we have here, I'll just add more notation. This system has a size D in our problem. The above equation can be general. So in principle, the current can be overall space, but now let us confine it to a system. And this is the integration volume, because the current outside of the volume is simply zero. So integration over zero is obvious. So this strange looking shape is what I mean by integration over this volume in principle. And then we define the origin. And then, okay, there is a small distance. This is R prime. To some point in space, I integrate over R prime. Then this is R minus R prime. This is where I'm looking at. The observer is here. And from the origin, I have R. So you see, this is this R prime. You move along inside the volume, you integrate over the whole volume. Easier said than done. Luckily, I'm not doing it, I'm just saying it. But in principle, you can always do it with a computer. Or if you are lucky, you can do it with a computer. Or in simple problems like ours, we can also solve it. What is the retarded time? Again, this is exactly what we had in previous lesson. It's the time, the local time, that this guy has some clock and he measures this time. This is the time t. And this is simply, in principle, r minus r prime over c. Again, r minus r prime over c is the time of information to go from r prime to the position c. So this is the relevant, at this relevant time, you care about the value of the current at a specific space, point in space in the system, right? So these are the ideas that we had in previous lesson. Again, R is for retarded. Okay, so what we are doing now in this approximation, what we are doing today is we are going to say that TR, the retarded time, is actually T divided by R over C. Why do we say this? We say this simply because if this is my system and this is D, and we are here at point R, and R is much bigger than D, then, you know, we have here some R prime. R prime is very small compared to R. Because R prime, absolute value, is of order D. What do I mean by that? R prime is an integration variable. It changes when I integrate, but at each point here, this is R prime, then I integrate, it's here R prime, etc. You go over all the space, but it's always smaller than R. So I can use this approximation. Okay, so let us have now 10 minutes break. I will continue the calculation of A. Then we'll have the fields. Then we'll have the density. And then we'll do it in full generality, not for the specific problem. Actually, the full general problem will be easier to do, but it's formal because we don't solve a problem. And it will give us very much wider insight. For example, that any accelerated charge can be used to create this radiation. Okay, so let us stop for a second here and come back another 10 minutes, unless you have some question now. No. Okay, so let's have a break. Okay, guys, is anyone out there? You had your coffee and you came back. Good. Okay, so I guess we should continue. 1 second. Yeah, so we want to calculate this vector potential A, and using this approximation for the retarded time, which is valid when the distances from the system has size D, are very, very large. Again, going back to our analogy, you are far away from me, and that is a good approximation in many cases. Now we need to define what is exactly the current in our specific problem. Actually, to define the current is not so trivial in our problem in my mind. But anyway, I'll try my best to explain what I mean by current here. So we have here this is just a reminder, and we have here minus Q of T. And we think about a kind of a wire that goes between them. So we can ask, what is a delta Q on the top? The top is plus the, okay, maybe we'll have top here, down, or up and down. Top guy. This is simply the change of the charge in a small interval of time. This is, of course, cosine. This is definition of the model. I mean, I'm just putting here what is the charge at time t plus delta t minus the charge at time t. So this is the change of charge on the top for time delta t. And it's a small change. Delta Q is small because delta T is small. And you all see by Taylor expanding that this guy is equal to minus Q times omega delta T times sine omega T. Why do I say this? Because I'm just doing the Taylor expansion of the cosine. The Taylor expansion of the cosine is the sine with a minus term. And this is on top. And delta Q on the bottom is exactly the same, but with a plus sign because of this minus here, plus Q omega delta T sine omega T. So what is the current, let's say, on the top? Is this simply delta Q over delta T. And this is simply minus QW sine omega T. And the same for the bottom. Let's write it in absolute value. So this is the current that I'm thinking about. And then I need to think about the current density in 3 dimensions and relate it to this 1-dimensional configuration. So I'm going to write it like this. This is a delta function of R cylindrical. So we have, this is our dipole. And I'm actually using here kind of cylindrical, this is this distance This is not the position of the particle, but rather the charge current along this wire. So this contains in it, if you want, so here is z direction. This contains in it the xy plane. I mean, it's simply saying delta x squared plus y squared is equal 0 along this thing. And this one is z plus d over 2 minus delta z d over 2. Did I get mixed up with the signs? I of t. So we have on the bottom and on the top, but this is actually the top. I think it has to be like this. And I of t is simply no, I of t is minus q omega sine omega t. Is this more or less clear? Okay, and then when I integrate, I plug in this j, I get the following, that I integrate over delta functions. So I'm integrating over all space. So this is A in this dipole, oscillating dipole approximation is equal to Q0 I T minus R over C. So this is the retarded time, 4 pi R times D. So I'm going to use this. But let me explain what is done. I just go backwards a bit. You see, in this TR, because we are at this approximation with T minus, the retarded time is simply T minus R over C because we are far away. I just plugged into this I, this retarded time here. Where did I get the D from? I got the D from the integration over all space that is done here, this integration. I get this D, and U0 over 4 pi, of course, comes from the usual thing. So this is what you finally get by a simple integration. So I can write this A for our specific model as minus U0 P0 W sine omega t minus R over C divided by 4 pi R. Oh, I forgot to write. Of course, the direction here is Z. Why the direction is Z? Because the direction of J is the same direction of the current, and that is the direction of the dipole. This is, of course, very important. All this multiplied by Z. So again, here I see the retarded effect, that is the time that it takes to reach point R. This is R, not R prime, because I already integrated. This W comes from the fact that we are using the current, and the current is proportional to the change of the charge on each one of these spots up and down. So that gives you time derivative, and that gives you this omega here. It's going to be important. And 1 over R, it comes simply from the fact that we have here R minus R prime, but R prime here is of order D or smaller, and D is negligible compared to 1 over R, and that's why we got this expression for A, which is again a simple expression. Of course, when frequency omega is equal to 0, we have no effect. We know that because we know that if there's no current, there is no magnetic field, and then there's no phenomena whatsoever. We also see, this P0 is important. It's just, if there's no dipole, there is obviously no effect. So now we have to calculate E minus div V dA dt. At last, we can calculate the electric field. The electric field, I want to start with the calculation of dA dt. What is the direction of dA dt? It's in the direction of Z. So we have the dipole, and it's up. So this is the dipole, the current. A is going in this direction. Taking the time derivative is easy. I'll take the time derivative, and then what will I get? Instead of the sine, I'll get a cosine. So let us write it. It's minus U0, P0, W. What will happen to W now? Maybe we should emphasize this. Okay. Squared. 1W here, and another from the derivative. This square is going to be important later. Then we have cosine cosine omega t, this retarded effect. This is when you take the derivative of a sine, you get a cosine, obviously. So I took the derivative with respect to time of this sine. And now I'm going to write the z direction as the following. Cosine theta r, this is in spherical coordinates, minus sine theta theta. So all this junk is simply the z direction. And what is important is, you see this, this is related to the hint I gave before. Hint before, dv gives r component. You remember this? We talked about it. It was from this d over dr r from the div. But you see also here I have an r component. So when you calculate the E, I'm not doing it, you have two contributions in the r direction. And what happens to them? They vanish. So components from div V and dA dt in the r direction cancel out. I didn't prove it because for me it's obvious. Not obvious. Okay, I'm used to it, but it's obvious because we understand the S is going radially and E is perpendicular to this direction of S, perpendicular to the sphere, to the element of the surface, perpendicular to the sphere that we had in mind. So we know this because S is perpendicular to E, to be expected. I put it in parentheses because I guess the first guy who did it was really amazed by this fact. Summing up, what I get for E in our problem is minus U0 P0. Omega, again, this square is going to be very important, 4 pi sine theta over r cosine omega t minus RC in the theta direction. I think you all know what I mean by theta direction in spherical coordinates. If not, go to chapter 1 in Griffiths. It's of course orthogonal to R, the small vector R, and of course also to the phi, but phi is not relevant in this problem. Where did we get this sign here? See this sign? This sign gives you this sign dependence of theta, and it's super important because it tells you how the dipole has to be oriented in order for it to be transmitting effectively. That is, if theta is equal 0, what will happen? Electric field is 0. What will happen to the magnetic field at theta equals 0?
Also 0.
We also expect, and this is also true, B is equal 0. That means S is equal 0. And that means that the P of R is also, well, not P of R, but SDA is 0. So again, I have my dipole, and I have here, so this is the Z direction, right? Theta equals 0 is up here or down here? Up here, E is equal 0. So where will the radiation eventually go? It will go mainly in this way. This way is when theta is equal 90 degrees. Up here, it's when theta is equal 0. Okay, so we already see something. So where does the W2 term? This comes from current gives W, and then ddTA, because you have an oscillating function, gives another W. Omega, sorry. But the most striking thing, as I said before, E proportional, this is not alpha, to what? With respect to R. 1 over R. A huge victory. What I claimed. Again, remember the magic. There is no charges here. A static dipole will decay like 1 over R cube. But here we took into consideration the retarded effect, and we got this 1 over R. What is B? By now, it's not so surprising. Well, first of all, it is rotor A. I'm not going to solve this rotor A because you solved rotor A in many parts of this course. You know how to take the rotor A because I gave you A. In principle, you can do this exercise using spherical coordinates. It will give you something which you can guess. Maybe you cannot. I don't know. Someone wants to guess? Let us write it down. What do you think? It will be W to what power?
1 power, because it's like the integral over E by time.
You said 1?
Yes? To the
No,
power of 1.
2. Think why. Maybe you didn't. It's the same as this one. Sine theta over R cosine omega t R over C. Sorry about this. Multiplied in the phi direction. This is because of the rotor. You get this. So this is the Z direction. So the phi direction is rotating around. This is also what you expect. This is, I think, trivial. This is the retarded time. This is the beautiful physics that we had before, 1 over R. Sine theta as before. What is missing here?
Over C.
Exactly, very good. And why is that expected?
Because there was a cosine. There was a
You are
cosine.
a mathematician, but you are absolutely correct. Okay, continue.
You derivated the cosine of omega r over C.
Yeah, that is the correct thing, but it's also something that you saw in this class. That is, the B in absolute value is the same as the E
Yeah. Over C.
divided by C.
Yes.
This is not new in this class. Your answer is perfect, of course, but now I just want to connect it to what we said previously in the class, that B is proportional to E over C. Of course, B is also perpendicular to E because E is in the theta direction and B is in the phi direction. And if E is in the theta direction and phi is in the phi direction, what is S, which is E cross B? What direction it is? It has to be R, because when you multiply two vectors in two perpendicular directions, you get the third direction, which is R. So now we can write S as 1 over U0 E cross B. That's the pointing vector, which gives you, what is this? I just want to remind you, this is the energy per unit time per unit surface. That is, the units are a squared, the distance squared, flowing through R. So this is what I call the local. You have this sphere, you have this dA. If I want to multiply S by dA, this will give you the total energy per unit time going through this small element of surface on the surface of the sphere. But this is just a reminder. This is just a definition, and then S, I just take the equations that we had before, is U0 over C. Of course, here behind the scenes, I'm using the relation between mu0, epsilon 0, and C. That's why I wrote it a bit strangely. Maybe you didn't complain, that's okay. Here, this is with U0, but you can write it with epsilon 0 also. Maybe it's better to write it with epsilon 0, and then you will see here the C, because at this expression, you see immediately that when C goes to 0, C goes to infinity, there is no effect. If you write this expression, but not with U0, with epsilon 0, then you'll see the same effect here. So all the effects are, of course, relativistic effects, P0 omega squared. Okay, let us write it like this, 4 pi sine theta over R cosine omega t minus R over C, again, the retarded effect. All this to what? It's E cross B. So it's the same expression that we had here. And here I have these two, because I'm multiplying two functions, E and B. It's a nonlinear effect. You need both the field E and the field B. And this, as we said, is in the R direction, which is, of course, meaning that the flux of energy is going out perpendicular to the surface, the sphere that we have here. And what do we get here? So let us summarize what we see here. We have this, first of all, we have this dipole, which is time dependent. We have the big sphere, it's ellipse, but this is only because I'm driving. I'm floating, and here S relatively large. Here S up here or down here, 0. Because of this sine theta. Again, this, we said it already. Here theta is 90 degrees. So if you want to receive And if this guy is the z direction, you want to receive it here, not down here. Now, we still have this cosine. I mentioned this cosine squared omega t r over c. And this is here, this term, when I square it. If I didn't square it, by the way, okay, if you go back here to the fields B and E, while, again, the miracle is that they decay like 1 over r, you see that they are also oscillating very quickly if W is very large. And this means that the time average of these fields, let's say you have a measurement device that doesn't measure at a specific time, but it measures over time, let's say over 1 minute, and it averages the result, this field E will be 0 because cosine is oscillating in time. It's sometimes +1, sometimes -1, and everything in between. But when I look at the flux at S, because I square things, because it's E cross B, I get this cosine square, which looks something like this. And the cosine is between 1 and 0, and there's some periodicity. And then in most circumstances, but not all, what you do is you take the average. It's an average over some periods, many periods, let's say. So the average over period over time, cosine squared omega t minus rc. So it means I integrate over time, cosine squared, and I divide by time t. Now, this was already in the classroom. We saw this before. Remember? Do you remember this? What is the answer? Yes. And we had it in the class. I mean, I talked about this before, so I'm not going to do it before. If you don't understand what is the meaning of this average over time, either ask me or go back to your previous discussion. So now, what is the P average? What is the meaning of the average? It's simply average over this very fast oscillations. This is equal to the integral over the surface of the sphere. What sphere? Again, I said it a million times, but maybe you don't know, you're already sleeping. This is the surface of the sphere, which defines the point where the observer is sitting. So we have this observer, we're somewhere on the sphere. And now I'm just looking at the average, not on the local intensity, which again depends on this sine theta. So this will be S times dA. And this is in R direction, and also S is in R direction. So first let us write average S. I didn't write it. What is average S? Again, depends on the angle theta. This is simply U P0 to the power 2, the dipole moment to the power 2, W, let's write it here, 4. Why 4? We had the square, and now we square it again. This square and this square, 2 times 2 is 4. So we have this, and then we have sine squared theta, because again, we are squaring thing. We have R to the power 2. Super important, because 1 over R to the power 2 will cancel the R squared that exists in the dA. Here I have R, and here I have 32 pi squared over times C. What is 32 is 4 times 4 times 2. What is the 2? That's from the averaging over time. And the 4, this is the famous 4. You multiply it by 2. So we get this 32 here. But it's not so important. We see this sign square theta because, of course, there is a symmetry. It cannot be sine theta itself. It has to be, it's a positive value for all theta. So this is the local, what I call the local flux at one point, which is defined by this theta. And then now I can plug this in and I can integrate it over dA. This is equal to the P of R. Again, this is the power. This is SdA with the dot over the surface. The surface is, again, a theoretical construction. This is equal, I can easily do this, U0 pi P0 to the power 2, W to the power 4 that we had already. This 32 pi squared times C. Integral from 0 to pi, this is the theta integration. Integral from 0 to 2 pi, that's the phi integration. So here I have sine squared theta. Again, this is this sine squared here. The R squared is canceled out. Then I have sine theta, d theta, d phi. Okay, let's write it down. R squared divided by R squared. Let there be Apple. Apple, the company, I mean. So this cancels. This is, of course, 1. So now we do a simple integration, sine to the power 3 theta d theta. It's very easy to solve this integral. You write the sine to the power 2 as 1 minus cosine to the power 2. And the sinus theta times d theta is d cosine theta. I'm not going to do this, but this is equal 4 over 3. Then if we look at all the numbers we have here, we have this 4 over 3 from this integration. We have 2 pi from the phi integration. We have this 32 and pi squared. All this gives 1 over 12. It's not a trivial number, times pi. And then the P, the power, average over all the sphere, is this famous equation U0 P0, so omega to the power 4, 12 pi C. So again, because I integrated over the angle, there is no angular dependence. This is the total power that is emitted. If you want to build this source of wave, you need to have enough power to put it in the system, so to say. This is, of course, not independent of the radius R, which is obvious. This is my whole point. And this is essentially one of the nicest equation that we have here. And this depends on the omega 4. Now, okay. So now let us have some small remarks. Or one remark. What we see here is that the power will increase with the frequency to the power 4. If you read Griffiths, he says, because of this, the sky is blue. What I mean by blue is blue in the middle of the day. This is, it's true, but it's also a bit of an exaggeration, and it poses several questions. So the general idea is we have the sun, and the sun emits what we call white light. White light, I mean, it contains a lot of frequencies, let's say within the visible range, green, blue, red, whatever you want, also ultraviolet, of course, many things. But then this light travels, this is Earth, and then it gets scatters. It gets scatters from what? It gets scatters from small molecules, maybe O2 or many other molecules that exist in the literature. These molecules have some size d. They are small. The point is molecules, even physicists know that molecules are small. They are much smaller than R. And within the range of visible light, they are also much smaller than lambda. So the conditions that we have, that we built the theory, are valid. If the antenna is these small molecules in the atmosphere. So what happens is the following. All kinds of sources come with all different frequencies. Here we have all the frequencies. But what is scattered better compared to other light, because of the W to the power 4. So let us compare two types of radiation. Let's say red and blue. Then the red has a frequency lower than the blue. And then the claim is that, and it's a claim, I mean, you should talk to chat to understand it better, in my opinion. The claim is that because it's scattered much more than the red, what you will see is the blue. Because the red is not, you see here I have something, it comes up here, and boom, it goes, and then it can go down, and you will see it, while the red is not, because of the W, the red is also scattered. By the way, when I say scattering, I mean that the frequency of the light coming from the sun, let's say it's red, it has some frequency, or it's blue, it has some frequency. You are not changing this frequency. So this is not like you studied in quantum mechanics where you absorbed some energy and then you emit it at the frequency of the molecule itself. This is why it's called scattering, and it has a professional name. This is called Rayleigh scattering. Now, we could argue till tomorrow if this is a good explanation. I mean, in textbooks, physicists are very proud that they can explain why the sky is blue. But you can ask some questions here. For example, why is it blue and not purple or violet? Because this argument will tell you, okay, blue is better than red, but why not purple or violet, which have higher frequencies, and then this frequency will be even bigger? Anyone wants to give an answer? Why is the sky blue? Why is it not purple, violet, whatever you want? Okay, it cannot be ultraviolet because we don't see ultraviolet. So, I mean, for me, this is not a good explanation why as a standalone, it might say why it's not red and it's more tendent to blue, that is fine. But why is it not purple or violet? Okay, then you need to ask ChatGPT, and ChatGPT says two things. One, the sun, I said before that it emits lights in all the frequencies. And I said it's white, which means all the frequencies are more or less the same. But this is actually not true. There is some preferences to blue over purple and violet. And that's why you see the blue and you don't see the violet. That's one reason ChatGPT gives you. So it's something to do with the physics of the sun and the emission spectrum of the sun, and not only of this general rule of this W to the power 4. And then ChatGPT also says your eye has more tendency to see blue than the violet. the efficiency of the collection of light is better in blue compared to violet. And this is actually something even I can understand, because you know that ultraviolet you cannot see at all. So you understand that your light vision is better in blue compared to violet, right? I think I understand it, even though I'm not a biologist. But this totally messes your mind up, because if you say this thing that, you know, I can see better violet compared to blue, then maybe you can see red compared to better than, it becomes a problem in biology and the physics of the eye. So, okay, you can argue again, but if you go to a pub and you want to impress some person and you can say to him, okay, the scattering of Rayleigh is omega to the power 4, then there is a preference for blue to be scattered, and then you will see more blue. That is absolutely correct compared to red. This is part of the story, but not all the story. The real life is very complicated. I then was bored yesterday, and then I asked ChatGPT, what about other planets on this in our system? Of course, we don't have, we never visioned many skies, or maybe at least I didn't. I only visioned one sky, which is our sky, which is blue, unless you are blind colored. So what is the color of the sky on the moon?
There is none.
No, there is none. You are right and you are wrong. There is a color. It's called black. But you are right, okay. And there's none, and the reason is, why is the reason? Based on what I said just now,
No atmosphere.
there is no atmosphere, and then there's nothing to scatter, and then this omega, there's no P0, so to say. So you see black. But if you go, for example, to Mars, there is a color for the sky, and actually I think you even know it if you have general education. And then there is another question. Okay, we have this color blue during the day, if there are no clouds, I mean. But what is it on Earth when you go to the sunset or sunrise? What is it? It's reddish, right? Okay, so on Earth, in the middle of the day, we have blue, and the end of the day, or I know that you all sleep at the beginning of the day, so I just say the end of the day, it's more romantic. End of the day, it's red. Middle of the day, it's blue. What is going on? Why is it red at the end of the day? Then what physicists will tell you is, oh, we can explain everything. What is the idea? We have Rayleigh scattering, this W to the power 4. So at the end of the day, so here is the sun. At the end of the day, I think you understand my point of view. This is night. This half is night. Now you are sitting somewhere here towards the end of the day. Now the sun is coming through a lot of atmosphere. Unlike in the middle of the day where you have one scattering event, not so many scattering events. But now it comes through a lot of atmosphere because it's on the horizon. If you ask ChatGPT how much atmosphere is in this situation compared to the midday, ChatGPT says 30 times bigger. 30 times more atmosphere to cross at the end of the day compared to the middle of the day. What does it mean? Say, much bigger, much bigger. What does it mean from point of view of this scattering? I said before, you have here this poor molecule that is scattering light towards you. What happens at the end of the day is you have many or several scattering events. And then what will happen to the blue? It's scattered more because of the W to the power 4 term compared to the red. And then all the red, because of multiple scattering, just goes somewhere. That is the claim, at least. You need to think about it. And then you are left with the red. So sunset is red because of this W to the 4. Middle of the day, W to the 4, because of the same rule. So, you know, it's like politicians. We can explain two things with one rule, but with different circumstances. So I'm just begging you, if you're interested, just think about this a bit more. It's a bit, in my opinion, this is real life, so it's very complicated. But this is what is the claim? And then you can ask yourself the following question. Let's say on the moon, the day is dark, the sky is dark. I mean, the sky is dark. It doesn't mean that there's no sunlight. You look at the sky, you see dark. And of course, in the middle of the night, you look at the dark, it's also dark. Because out there is no one, or nearly no one. Obviously, black and black. On the Earth, it's during the day, it's blue. At the evening, it's red. Now I have a question for you. What is it on Mars? During the day, during the night. There is an atmosphere, so it's not like the moon. Anyone has a guess? What is it during the day? This you should actually, I think you should know. What is Mars? What is the color of Mars?
Orange.
Orange or red.
Red.
Yeah, red, orange, red is the same. So the sky of, also for the observer that is on Mars, in the middle of the day in Mars is exactly the opposite of what we see. It's reddish. And what is it when you have the sunrise or sunset? It's bluish. It's the opposite, according to chat. I didn't know this. It's the opposite of Earth. Now, let us just focus on the day. Why is it reddish? What is the difference? There is an atmosphere on Earth. There is an atmosphere on Mars. What is there is a difference, however, between Mars and Earth. What is the major difference, a famous difference between the two planets?
The atmosphere more condensed or less.
Pressure is correct. The atmosphere is also correct. But all this is related to one thing, which is the mass of our planet compared to Mars. Mars is the mass of Mars is not so big compared to our mass. And that means, what does it mean on the atmosphere, which also implies the pressure? The atmosphere is thinner. I'm not talking about oxygen here, just some gas particles. The atmosphere on Mars is thinner. ChatGPT says 1%. But still, you have an atmosphere. And actually, what I said before was, if you have only 1 or 2 events of scattering, you will prefer blue light. So why is it still red? Anyone wants to get?
It is related to the fact that we are looking on Mars from the outside, so we saw what's scattered.
No. I asked ChatGPT, what will happen when you are on Mars? I'm telling you that if you go to Mars, the day will be red and the sunset and sunrise is going to be blue when you are on Mars. Opposite of Earth. But, you look at the theory that we said now, this W to the 4, you say, wow, it should be the same. So, let's see if you are smarter than chat. I'm not smarter than him. He's smarter than me. So what happens is the following. The atmosphere is different, but it's not only about 1% atmosphere on Mars compared to Earth. That is not the crucial thing. Because the mass of Mars is so weak, what will remain on Mars and what will leave Mars predominantly in its atmosphere? What remains there predominantly more than on Earth is dust particles. Dust. What are dust particles? They are much bigger than small molecules like O2 or N2. And we know this on Earth. How do we know this on Earth? When we have the bad weather towards Pesach, when we cleaned our houses and then we have these sandstorms, what is the color of the sky? Okay, you can argue yellow, red, but okay, for me it's red. It's reddish, and this is because of sand. And because sand is equal dust for me. That's not, don't tell it to any geologist, but let's call it the same thing. And then the question is, so what? What is the difference if I scatter from dust and if I scatter from molecules like O2? So again, on Mars, we have a lot of nasty dust. Again, the dust is remaining. What happens there? Maybe a long time ago, there was a lot of molecules on Mars, but they managed to escape because the mass is very small. So they can escape. These small molecules manage to escape, but the heavier particles, which are the dust particles, remain. So what happens? You have this dust. This is Mars. And now what happens? What it breaks down is that now D, which is the size of these dust particles, is of order lambda. Our theory is invalid. So I assumed that the dipole D, again, how does the dipole being created for molecules of dust? You have some light coming, it fluctuates these dipoles. So there is an impinging, it's a very complicated process. There is some light coming, it creates this oscillation of charges because of the incoming light. That is the frequency, and then you scatter more if based on this W to the power 4. But here, the basic condition doesn't hold. Our theory is invalid, and there is a different theory called me theory. And in this case, the physics is simply different. So the conclusion is simple. The atmosphere and the blue sky that we see here is related to Rayleigh physics. Rayleigh is this law that we had before, this W to the 4. And if you go on Mars, if you had a class there, not here, most likely the professor would be teaching you me physics and not Rayleigh physics if he wants to teach about the sky that you are used to. It just says that the condition is very important. I'm not going to teach me. It just says that, you know, this whole field is a very gigantic field. Okay, so now I have talked a lot about this example. We are going to stop now because I think all of us, especially maybe you, are tired. What we are going to do in the last lesson next week, which might be on Tuesday, because on Wednesday evening I'm going to some conference in Italy. So I will announce this. It might be on Tuesday or Wednesday, but what I'm going to do next week is simply, from my point of view, a continuation of this class. I don't want to do it now. It will be just do the same thing I did today, but with a general current. It's not going to be, in my opinion, difficult under the condition that you maybe repeat, understand what I said today, or read what you have in Griffiths. So our question is general theory related some source J to, let's say, A, and then to S, etc., and showing what are the general things of what we did today. That will be the final lesson, unfortunately. And maybe I'll describe also this formulation of Maxwell equations in tensor method, but I'm not sure I will have time. So again, this is a very sad day for us, but also yesterday was a very good day, maybe. I think so. Let us hope for better times, and thank you for your attention. I think there was someone who wanted to talk to me, so he's welcome to stay.
Thank you very much.
Thank you.
You're welcome.
Thank you.
Very much.
Thank you.
Yeah. So is someone with me?
כן, היי אלי.
מה שלומך?
ברוך השם, מצוין. אולי אבל נדבר אחרי שהם יצאו, או שיש כאן עוד מישהו שרוצה להיות לפניי?
כאילו, רציתי לשאול משהו, אבל לא רציתי לדעת אם ידעו כבר מה יהיה המבנה של המבחן.
אני אכריז על זה בשבוע הבא, אבל בגדול כל מה שלימדתי, אני מאוד רוצה שתלמדו רדיאשן, אבל כנראה זה לא יהיה במבחן. תזכיר לי בשבוע הבא להגיד את זה, אבל לפי דעתי אם אתה פיזיקאי רציני אתה תלמד מה שלמדנו היום. פשוט ביקשו מאיתנו לחתוך קצת את החומר וזה בא בסוף, אז אני אתן לכם את הרמז שזה לא יהיה, אבל זה, אני יודע שאתם מאוד עסוקים, זה ממש מכאיב לי שזה לא יהיה חלק מהמבחן.
לא כמה שאלות יהיו, או כאילו, זה יהיה דומה
בינתיים
לשני.
יהיה לפחות 3 שאלות, אני לא יודע אם אני אכתוב את הרביעית, זה תלוי קצת, נראה.
אוקיי, טוב, תודה רבה.
להתראות. כן, עכשיו אני חושב שאנחנו לבד, חוץ מ... אבל אני לא חושב שיש פה סודות.
לא, סבבה, סבבה, סתם לא להעלות את האנשים. אמ, ככה, אז טוב, אז כתבתי קצת במייל, שאני עכשיו מסיים תקופה של מילואים, ומיד אחרי זה חתונה, ברוך השם, שקצת הוציאו אותי, המילואים אבל הם התקופה העיקרית, אז כאילו, אמ, אז יש לי בעצם איזשהו פער בקורס, והשאלה אם יש דרך, או איך נכון לגשת לזה בשביל באמת להשלים ולא לא להחסיר כאילו מהחומר הנדרש כזה.
טוב, אז כמו שאני אמרתי באימייל, אז אני מאוד מעריך כל מי שמשרת במילואים. אני לא רוצה להישמע ציני, אבל העניין של החתונה זה לא מעלה מבחינתי ולא מוריד, כי היכולת לקבוע את החתונה לא על תקופת הלימודים, אבל אז בוא לא נדבר על זה בכלל. אז כמובן, כמה זמן היית במילואים?
40 יום כאילו בסך הכל.
בסדר, ואני מבין לחלוטין שלאחר 40 יום אתה צריך להיות טיפה עם המשפחה שלך, אתה צריך להירגע, זה מקובל עליי. אז קודם כל בתקופה של ה-40 יום, בתקופה עצמה של המילואים, אז כמובן אתה לא צריך להגיש תרגילים, או בעיניי לפחות, אני חושב שזה הנוהל מקובל בכל האוניברסיטה, אתה לא צריך להגיש תרגילים. זה
כן.
שאתה מגיש אותם, האם זה טוב או רע, זה כבר סיפור אחר. אני רק אומר מה הזכויות שלך בתור מילואימניק. אתה צריך להודיע למתרגל שלך. מי המתרגל שלך?
אני לא סגור מהם, אבל אני אדבר איתם.
אוקיי, אז תשלח להם אימייל ותודיע להם מיום זה עד ליום זה הייתי במילואים, אני מבקש מכם לא שאתם
לא להתחשב בהם.
אז מה שאנחנו עושים בסיום הקורס, אז לדוגמה אתה מפספס לדוגמה לצורך העניין 5 תרגילים, אז אנחנו ממצאים על התרגילים שכן הוגשו וכולי. עכשיו אם אתה בא ואומר לי אני צריך להתאושש ממילואים בגלל שוב יכול להיות שהסיבה שאתה רוצה להיות עם אשתך זה לא מעניין אותי מה הסיבה, אני לא רוצה שתסביר לי למה, תגיד לי אני צריך עוד שבוע להתאוששות, אין בעיה, תגיד לי את זה ותכתוב להם 40 יום הייתי במילואים ואלי אישר לי עוד שבוע, אתה יודע,
כן,
להתאוששות.
אין בעיה.
אתה מבין?
כן, תודה רבה.
אין
אבל
בעיה.
אני רק, נגיד, כתבת איזשהו מתווה שאולי נעשה בהקשר לבחינה.
רגע, לאט לאט, אני דיברתי עכשיו רק על השיעורי בית.
כן, לא, זו שאלה על שיעורי בית בעצם.
אוקיי.
נגיד אני עכשיו מתחיל ללמוד בעצם את הקורס מההתחלה, אז התרגילים שכרגע פתוחים לי הם לא רלוונטיים לחומר שאני לומד.
אוקיי, אז צריך
אני
לפתוח
אגיע
לך
לזה
את
רק
התרגילים.
בהמשך.
אז אתה אומר שצריך לפתוח לך את התרגילים. מה זה לפתוח? לפתוח בלהגיש או לפתוח? אוקיי, רק שנייה, תן לי להמשיך עוד קצת.
אוקיי.
אני חושב שאולי אני אענה על השאלה, ואם לא תשאל עוד פעם. עכשיו, מה
אוקיי.
שאמרתי פה זה, התייחסתי לנושא מההיבט שמבחינתי, היבט פורמלי שזכויות שלך, כמו בהסתדרות, מגיע לך משהו ואתה מקבל את זה, זה ברור מאליו.
מהמם.
השאלה היא האם זה הצעד הנכון בשבילך לא לעשות את התרגילים האלה בכלל. אז באופן אידיאלי אני ממליץ לך בתור פיזיקאי כדי לעבור את המבחן תעשה את שיעורי הבית, זה הרבה יותר
כן.
חשוב מאשר זה. עכשיו אתה יכול להגיד לי אוקיי אבל יש לי בעיה של זמן, זה כמובן, אז את הבעיה הזאת בוא נדבר עליה עכשיו. העצה שלי אליך באופן כללי כדי לעבור את הקורס בציון טוב זה כן לפתור את שיעורי הבית, עכשיו, שטוב, ברור לנו שאתה לא יכול לפתור את כל שיעורי הבית, אז הדרך הנכונה לעשות את זה, זה פשוט להתחיל מתרגיל 1, 2, עד איזה תרגיל הגשת?
חושב 3.
3, אז אני הייתי ממליץ לך להתחיל, קודם כל הקורס הוא בנוי מהקל לקשה, אז עדיף שתתמקד בקל ותבנה לעצמך את הבסיס ולא תמהר. אז נגיד 1, 2, 3, מתי המבחן? יכול להיות שידחו אותו?
המבחן הוא ב-22 ליולי. זה אומר עוד חודש בערך.
עוד חודש. אז אני הייתי אומר כדי לא להעמיס עליך, אני לא רוצה שתעמיס עליך, זה לא בריא לנפש וזה לא בריא לפיזיקה אפילו, מה שאני הייתי ממליץ לך, אבל זה תלוי בך, יש לך 3, עד תרגיל 3 תעשה 4, 5, 6, 7, אולי תגיע לחלק המעניין, ואז יש לך תרגיל בשבוע לעשות? אתה איתי?
4, 5, 6, כן.
אתה יכול להגיש אותם, אבל לא נוכל לבדוק אותם כי הבודק תרגילים לא יהיה, אולי הוא יסכים לבדוק אותם לאחר ההגשה, אין לי שום בעיה אם אתה מגיש אותם במקום שאתה מגיש את האחרונים. זה
אוקיי.
מוביל אותך לתרגיל 7 זה בעצם עדיין המבוא של הקורס, יש עם זה בעיה, יש עם זה בעיה, כי זה עדיין המבוא של, זה מתחיל, זה התחלה של החלק השני של הקורס, שהוא החלק המעניין. היתרון של השיטה הזאת ברורה, אתה בונה את היסודות שלך ואתה עושה את זה לאט, אתה ניגש למבחן, ואז יהיה לך במבחן כמה שאלות, אתה פותר את השאלות שהן רלוונטיות לחומר שלמדת. אתה מקבל ציון, במקרה הטוב, נגיד אתה מסוגל לענות על 1 או 2 שאלות, בסדר, אתה פותר 1 או 2. אחרי זה אתה ממשיך בקיץ, אתה לומד מתרגיל 7 עד לסוף, ואתה ניגש למועד ב', במועד ב' אתה פותר את השאלות על החומר החדש.
כן.
אנחנו בסוף עושים ממוצע, אתה מגיש ערעור, עושים ממוצע ואתה תקבל את הציון שזה הממוצע בין שניהם.
אוקיי.
תחשוב על זה, אתה לא צריך לענות עכשיו, זו אופציה. למה האופציה הזאת טובה? האופציה הזאת מאפשרת לך, בעיניי היא מצוינת, עשיתי את זה בעבר עם סטודנט, היא מאפשרת לך עכשיו ללמוד בקצב איטי, בצורה יסודית, בלי להיות בלחץ, תוכל להתחתן ברוך השם וכולי, בלי לקרוא את עצמך. אני לא מאמין שאפשר ממש ללמוד מהר, אני לא מאמין בזה כי החומר מסובך בעיניי, אז צריך זמן לחשוב על הדברים. אתה גם יכול להיעזר בחברים שלך שלומדים למבחן עכשיו, רוב הקבוצה, אתה מצטרף לאיזושהי קבוצת לימוד ואתה לומד איתם, אבל אתה לומד על חלק מהשאלות יחד איתם, בעוד שאם תעשה את זה במועד ג' כבר לא יהיה לך עם מי ללמוד.
כן, נכון.
אז זה היתרון של השיטה הזאת. אתה יכול, אם אתה רוצה, לפי החוקים של האוניברסיטה, ואני מכבד את זה, לגשת למועד ג'. זה זכותך המלאה, ואם זה מה שאתה רוצה, בסדר גמור. יהיה מועד ג', אבל זה, אנחנו לא נדבר על זה עכשיו, אני לא כתבתי את מועד ג', ועוד חזון למועד, זה יהיה עוד הרבה זמן, יהיה לך, אני חושב שאתה מחויב לגשת אני חושב שמגיע לך מועד ג', אני לא בטוח ב100%, אני כמעט בטוח שמגיע לך.
כן, כן, מגיע לי. כן.
אז אתה תקבל מועד ג', אין שום בעיה. אני רק אומר
אני מעדיף לא לעשות אותו, כן? אבל כן, בוא נראה.
וגם אני מעדיף שלא תעשה אותו. לכתוב מבחן מועד ג' לבן אדם, ואחרי זה אתה צריך לבדוק את השאלות, אני מעדיף שלא תעשה, אבל אתה אל תתחשב במה שאני מעדיף. אני מציע לך את השיטה הזאת המדורגת, מציע לך לא להשתולל, לנסות ללמוד לעומק. אתה לא חייב לענות לי עכשיו, אתה יכול לחשוב על זה, מה אתה רוצה. אתה יכול
כן.
לנסות את השיטה ולהודיע לי בהמשך מה אתה מעדיף. אני לא זוכר, אני חייב להגיד לך את הדבר הבא, שהמבחן הוא כן יהיה יותר ממוקד, או לפחות בחלקו, על החלק השני של הקורס. כי אתה רואה את זה, לדוגמה היום ראית את זה, החלק השני של הקורס הוא הפיזיקה שהיא יותר חדשה לעומת מה שלמדתם בעבר, אולי בחשמל. שלמדתם שם קצת אלקטרוסטטיקה. אני לא טוען שמה שלימדתי זה אותו דבר מה שלמדתם בשנה א', אבל יש קשר בין הדברים. הטכניקה קצת יותר מתוחכמת, אבל הבסיס היה לכם כבר בעבר. אז הדברים החדשים בעיניי זה קרינה, אוקיי, אולי זה לא יהיה, אבל שדות שתלויים בזמן, שזה מה שלמדנו בשבוע שעבר, פוינטינג וקטור, כל הנושא של פתרונות של משוואת מקסוול עם ה-retarded time, כל הדברים האלה, זה לב העניינים. זה לא אומר שלא יהיה שאלות על תחילת הקורס, אבל אולי תבדוק מה בדיוק, מה היה בתרגיל 7, אני לא זוכר. תבדוק את הנושא הזה. אז אולי עדיף לך לא בדיוק 7 אלא 8.
כן. אוקיי.
בוא נדבר אחר כך. תסתכל על העניין, תסדר לך את החומר. אני חושב שב4 שבועות, אני לא יודע אם אתה סטודנט טוב או לא, אולי בגלל החתונה זה יהיה לך מאוד קשה. ב4 שבועות אתה כן יכול אולי להדביק את הפער. זה תלוי באיכות שלך וביכולת שלך להתרכז. אני יודע שאני בחתונה שלי לא יכולתי להתרכז הרבה, ואשתי עוד פחות, והיא שיגעה אותי. אז
כן.
בכל משפחה, זה ברור לי. מעבר לזה, בעקבות המלחמה שעכשיו נסתיימה, היה קשה להתרכז, ועכשיו יש עוד בטח, אני יודע שאם אתה היית בשירות, אז אולי יש לך חברים שנפגעו בכל מיני דרכים, אז העולם מסובך ומורכב, אז אני לא רוצה לקבוע איתך, אז תחשוב על זה, תבנה לעצמך איזשהו משהו. מה שכן חשוב לי מאוד, שאחרי שאתה סגור עם עצמך מה בדיוק אתה רוצה, תכתוב לי אימייל ותפרט בדיוק מה
אוקיי.
אמרנו פה. תגיד לי, אני אלמד עד זה כולל זה, אני אגש למועד ב', אני אגש למועד א', ב', או אני רוצה רק ג'. פשוט תגיד לי שאני אוכל להתכונן. אולי אני אצטרך את האישור של יוסי על זה, אבל הוא נתן לי בעבר, אז לא תהיה בעיה.
אוקיי, בסדר.
וזה יהיה פורמלי, כלומר, אם תבוא אליי עוד חודשיים אני עלול לשכוח, אז אני רוצה את זה באימייל מסודר, ונסגור את העניינים האלה עד הסוף.
אוקיי, מצוין. עכשיו, מבחינת החומר, כן יהיה לי יותר קשה להשלים אותו באנגלית, והקורס היה השנה באנגלית. השאלה אם החומר יחסית מקביל לשנים שעברו, ואני
ההתחלה
יכול...
של הקורס, ההתחלה, אבל הסוף לא, כי היו שנים שזה כן הגביל, אבל מה שאני מצאתי על האינטרנט, זה קורסים מתקופת הקורונה, ואז הסמסטר קוצר, ואז החלק החשוב של הקורס פשוט לא קיים שם.
הבנתי. אז
מבחינתי האנגלית זה דבר חשוב, זה חשוב לך לעתיד שלך, בין תהיה באקדמיה או תהיה מחוץ לאקדמיה. אני הדגשתי את זה, בשביל זה אני אומר תלמד לאט באנגלית כדי לדעת לקרוא טקסט, מה יש תרצה לקרוא מאמר. שוב, אני לא מכיר את האיכויות שלך בתור סטודנט, אבל הקריאה הזאת, אני הדגשתי את זה הרבה פעמים, היא סופר חשובה לעתיד שלך. יותר חשובה אולי מלדעת עוד קורס.
כן, לא, אנגלית זה חשוב, פשוט בגלל מסגרת הזמן הצפופה, אז אני כאילו אומר, אולי אני אקל על עצמי לפחות בנושא הזה.
אני מבין, אבל שוב, אני לא יודע מה איכות האנגלית שלך, אבל מה שאני מנסה להגיד כל הזמן זה, אני ממליץ להתקדם לאט, לא לתפוס הרבה, תפסת מרובה לא תפסת. עדיף לי שתלמד טוב את הדברים שאתה יכול, אבל בצורה כמו כל הסטודנטים, עדיף שתדע משהו טוב ותעבור את החוויה של כל הסטודנטים, ונגיד משהו בסוף לא השלמת, בסדר, זה עדיף לי. כמו לדוגמה מה שלמדנו היום, אז כנראה זה לא יהיה במבחן כמו שרמזתי. חבל מאוד, אבל עדיף
כן.
להעמיק, עדיף לקרוא. זה הגישה
אוקיי.
שלי.
בסדר גמור. תודה רבה.
להתראות,
תודה רבה.
ותודה לך על
להתראות.
השירות מילואים, ותשמור על עצמך, ומזל טוב.
אמן. תודה רבה. טוב.